Hi, welcome to Slay the PE's Mechanical Engineering PE exam review videos. This is the Energy and Power Systems module, and the video is Mass Balances 3. We recommend watching these videos in order, so if you have not reviewed Mass Balances 1 and 2, you should consider going back and watching those. Otherwise, let's get started. Alright, so as a review of what we learned in Mass Balances 1 and 2, we discussed the concept of mass flow rate and its relationship to the average fluid velocity through this equation rho AV, its relationship to the volume flow rate V dot, and there's another way to write these equations, which is this third one here, using the specific volume V. The specific volume is simply the inverse of density, and you'll see it specified with units of cubic feet per pound, or cubic meter per kilogram. So it gives you an idea of the volume that is occupied by a unit mass of the substance. So that'll come up later in the thermal discussions. Okay, so let's get into actually obtaining the mass balance equation. So consider this example. It's an atmospheric storage tank, and the way it's depicted here has one inlet, one outlet, and an atmospheric vent. Okay, so if we take a cross-section of it and take a snapshot at some instant t equal t0, we see that we have some mass here, at time equal t0, and then after a certain amount of time delta t has elapsed, we have a different mass, right, at t0 plus delta t. So there has been a change in the mass, okay, as time went on by an amount of delta t. So the basic conservation of mass principle is that change in the mass of the control volume, we're going to call delta m in the control volume, is simply the difference between the mass that was deposited into the control volume minus the mass that was withdrawn from that control volume during delta t. Okay, so for example, let's say initially we had 1,000 pounds of liquid, and then at the at delta t, at time equal delta t, then we had 1,100 pounds. Okay, so that means the difference in the mass, right, across delta t is 100 pounds. Okay, so if we have information about the mass that was put in during delta t and it happens to be 300 pounds, okay, then from this we know then that m out, or the amount of mass that left the control volume during delta t, has to be 200 pounds. Okay, so it's an accounting problem, really. You can see this as money in your bank account. So if you have $1,000 and after a month you have $1,100, the net change is a positive of 100. But during that month, you received 300, then you must have spent 200, right, for there to be a net increase of 100. Okay, so that's the basic principle of mass conservation. Now, if you take this equation and divide it by delta t on both sides and take the limit as delta t goes to 0, we can show, we're not going to do it here, but we can show that we obtain this expression, which is known as the rate form, which is quite more useful for problems, especially in the PE exam. The rate form essentially says that the rate at which the mass of the control volume changes with time is the difference between the rate at which mass enters minus the rate at which mass leaves. Right? Indeed, if you have a mass coming in at a rate, say, of 10 pounds per second, okay, and the mass coming out is doing so at a rate of, say, 8 pounds per second, okay, a pound mass per second, therefore the rate at which the mass is changing within the control volume is 2 pounds per second. Right? If you're putting in at 10 pounds per second and leaving at the rate of 8 pounds per second, then it's entering at a rate that is greater than the rate at which it's leaving. So you have a positive rate of change with time of the mass in the control volume. Okay, so that is the equation that we're going to use quite a bit, the rate form of the mass conservation statement. So what happens when in a bit more realistic setting you have multiple inlets and outlets as shown here? Well, the equation is the same, but instead of a single m dot in, we call the sum of the entering rates, right, m dot in number 1, number 2, and number 3, you add those together, and you call that the total rate of mass entering the control volume. So the time rate of change of the mass within the control volume is simply the difference between the total rate at which it enters minus the total rate at which it leaves. Okay, so let's quickly recap the mass conservation equation. That's the most general form. There are even more general forms which were derived for you in school when you took engineering thermal, but those are really just beyond the scope of the PE exam. This is good enough. Okay, and then there are special cases. One is the case of steady state. So the steady state is the situation you have when the rate at which the mass enters equals the rate at which it leaves. Therefore, there is no time rate of change of mass within the control volume. So if you have a control volume and it is entering at a certain rate and exiting at a certain rate, and there's a certain amount of mass here, even though we have flow in and out, the amount of matter inside the control volume does not change with time. So that's called steady state, and the vast majority of problems in the PE exam are going to be steady state. Okay, so it just tells you the rate at which it enters must equal the total rate at which it leaves. And then there are many control volumes that have only one inlet and one outlet. So in that case, we can drop the summation signs and then go straight to the equation that relates the mass flow rate with the velocity and the area, and we obtain this. So this one is also quite common, but you can see it's really just a special case of this. And then there's even more simplifications we can do, and when we're dealing with incompressible substances, which would be liquids or gases under certain conditions, which we will discuss later. Sorry, not zero. The density cancels out, right? For incompressible substances, you don't need to consider density, and we can talk about conservation of volumetric flow, but only in the case where the density doesn't change. Okay, the more general and preferred form is to work with this. Okay, so let's look at an example to solidify these concepts in your brain. So here's the example. At this point, as always, you are free to pause the video and attempt the problem on your own. Otherwise, let the playback continue and we will solve it here in real time. So we're back with the garden hose problem. But now the question is a little bit different. They're giving us the velocity at the tip of the nozzle, but the question is the velocity in the hose upstream of that nozzle. Okay, so this time there is superfluous information, which is the volume of the bucket. We don't need that. Okay, what we're going to do is apply the conservation of mass for the nozzle and figure it out. Okay, so let's make a little sketch of the information that we have, which will be this, right? There's a nozzle, which is a reduction in the diameter. It goes from 0.8 inches to 0.3 inches. The red dotted line represents our control volume. So we have this section here we're calling section 1, and this section here we're calling section 2. So the mass conservation equation is this. We have one inlet, one outlet, and here's the other thing. When the PE exam problem statement it will never say steady state. So if it doesn't say that, that is a quite safe assumption for you to make. That is steady state. If it is not a steady state problem, it would be very clear from the problem statement. Okay, so assuming then that it is a steady state, this would be the equation that we're using. So since the water is incompressible, we can cancel out the density. There's no change in density from section 1 to section 2. So we can just work with AV at section 1 equals AV at section 2. Okay, so then we would write that, right? The area at section 1 is pi divided by 4 times 0.8 inches squared times the velocity 1, which is what we're after, must equal the area at section 2 times the velocity at section 2, which is given as 50 feet per second. Now, so then you will use this equation and solve for V1. So here, it's really not necessary to start converting units. Let's see, first we can cancel out these pi divided by 4, and then when we solve for V1, the ratio of inch squared over inch squared is going to take care of itself. We don't really need to convert those inches to anything. So what we're going to get is 0.3 divided by 0.8. We can skip writing the inches because they're going to cancel out. And then we have our 50 and then feet per second here. So this means that we are going to get an answer in feet per second. Check quickly the question, and it does say feet per second. So we don't need to do anything else beyond crunching numbers here. If you do that, you're going to get about 7 feet per second. Okay, so in this case, the correct answer would be A. So to recap, the approach for this problem was defining the control volume, identifying the inlet and outlet ports in the control volume, and associating the information given with those locations. Okay, so the next video, Mass Balances 4, we will do some more examples of several situations you might encounter in the exam with mass balances.